Hello everyone, today we are going to talk about forces. Now, the topic, the study of forces is called dynamic. It's the study of why something moves. Now, so you should have heard about forces in previous science, so for example, science 10. So what is a force? Now, so the simplest way to explain this, right, is that a force is any type of a push. So it's any push or pull. So if you push or pull something, then there's a force. Okay, so whenever you push something or you pull something, so you need to use the force to do it. So for example, if you have a box on the ground and then you're trying to make the box move in some direction by kicking it, right? So let's say that's your feet. It's a feet because I say so. So what do you need to do to push that box? You need to apply a force, right? So we will say that, so let's say you want to move the object to the right-hand side, then you apply a force that's pushing the object to the right-hand side, right? So that is called a force. So your feet kicking the box to the right-hand side is a force. Now, as you see that in here, we do care about direction, because if you kick the box to the left-hand side, something very different will happen, right? Or you pick that box up by pulling it upward, something very different will happen. So a force is a vector quantity. So you do the direction to go with force. Now, the unit for force, so when we measure force, so when we measure distance, for example, it's measured in meter. Time is measured in second. Well, what's force measured in? Force is measured in the unit that's named after a very famous scientist, Isaac Newton, who studied a lot about forces among various other things. But he was the first one to write down an equation that actually can describe the force of gravity, not just on Earth, but even in space, for objects like the sun and the moon and how they attract each other and the planetary motions. He was able to explain that, even though he was born like 300 years ago, when there was no airplane and no one has ever been to space yet. He was able to generate that kind of knowledge from just his observations on Earth. So Isaac Newton was a pioneer physicist in this field. Therefore, we name the unit of force after him, Newton. So we call the force Newton. That means we can have a force of 1 Newton, 2 Newton, 1,000 Newton, 500 Newton, and so on. So now, of course, we have to have something in comparison, right? So how much is 1 Newton? So all of you have a cell phone, right? If you try to hold your cell phone out with your hand, just stick your hand out and put your cell phone there. And try to move your hand up and down. Now you feel a force from the cell phone pushing your hand down, right? So for example, if you relax, the cell phone is going to drop. So you have to hold on to it, right? So you feel that feeling of a force pushing down on your hand that's holding the phone. That is approximately 1 Newton. I mean, usually when we do this example in a regular class, I will ask the student to hold an apple, because of the famous story that I guess it was a story. No one knows if it really happens or not, that Isaac Newton sat under a apple tree and an apple falls onto the ground, and he was observing that, and then he has this idea that, hey, how come everything is falling to the ground, falling down? What's happening? So the rumor has it that, this is how he started his study and thinking about gravity, and eventually came up with all these equations that we're going to learn, and some of them we have already done. So Newton. So 1 Newton is about the weight of an apple on your hand. Since you don't have you might not have an apple, I just asked you to use your phone. So that's 1 Newton. So 1 Newton is about the weight of an apple dropping to your hand. Now, if someone say, I can punch with a force of 400 Newton, what does that mean? That means I can punch you with a force of 400 apples. Okay, so imagine you're lying down on the ground and someone put like 400 apples on you. That's the same force as some punches, right? Okay, so what other forces are there though? So the force that force is measured in Newton, but what forces are there in the universe. So there are actually only 4 forces that physics people are concerned about that makes up the entire universe. Only 4. The first one is the one that we already kind of mentioned in the last chapter, which is called gravitational force, which is the force of gravity. And you study this in Physics 11 and Physics 12, right? So this is the force that is attracting everything to everything else with mass. So later on, we'll go a little bit more detail around it. So, but for now, at this moment, just understand this. We are attracted to the Earth because of force of gravity. Anything with mass attracts each other. Since near us, right, as human being, the most massive object near us right now is the Earth. The sun is really far away, right? So therefore, we feel the Earth's attraction onto us. And that's force of gravity. It attracts everything to the center of the other objects. Now, and then the second force that also is responsible for our existence, I guess, is electromagnetic force. So it's not electric force only and magnetic force only. It's called electromagnetic force. Okay, electromagnetic force. Now, this one is the force on, like, for example, magnets, right? So I'm sure you have played with North Pole, South Pole, those little bar magnets, or maybe the one that's sticking to your fridge. So you know that there are forces associated with that, right? For example, North and South will attract each other. But if you put the 2 North Pole against each other, it will repel. So this is the kind of force that is called electromagnetic force. So of course, this is the magnetic version. There's also the electric version. So for example, if you put an electron and another electron together, what happens? They will repel, right? So electromagnetic force is this kind of force. Now, this is the force, electromagnetic force, right? It's the force that gives you the entire subject called chemistry. Chemistry is a part of physics that only deal with one force, the electromagnetic force. Now, regular physics, like physics, we look at all of them. But specifically, electromagnetic force is the force that's actually giving you all those chemical reactions. So, for example, if you study chemistry 11, you know, like protons and neutrons, and you know about the periodic table, you know about, the valence shells of electrons. The reason why, like, ionic bond or covalent bonds exist is because of electrostatic force, right? Because they want to share electron. One atom has extra electron, so it is negative. The other atom has extra proton, so it is positive. So therefore, these two stick together because one is negative, the other one is positive. Then they attract. That is electric force. So chemistry is basically just a special case, not a special case, a focus area from the electrostatic force portion of physics. Now, of course, in physics, we also study electrostatic force, but we don't look into the chemistry portion of it. We look even smaller. Like in chemistry, they look at how atoms are formed, like how atoms come together and form different molecules, right? How elements come together and form molecules. In physics, we look deeper into that. We actually look at what is inside the elements, inside the atoms, the protons, the neutrons, the electrons. In chemistry, they want to look at molecules, right? They want to look at the element, which is already an atom. So not, in some situation, you might care about how many protons, neutrons, and electrons there are, but you never take them apart. In physics, we actually take them apart and look at the inside. So this, however, will be covered in Physics 12 only. Okay, so not this year. Electrostatic force is covered in Physics 12. Now, other than those two, so gravity holds the entire universe together. I mean, this is the reason why we have planets and satellites and galaxies and universes. It's because of gravity, right? And the reason why we have any compounds And, in addition to just basic proton, neutron, and electron, the reason why we have things, right? We have all these materials on Earth is because those molecules those atoms can come together and form like molecules, and, elements can come together and form different types of materials, and that is electrostatic force. Then you might say, okay, Mr. Chang, that pretty much cover everything. So we have all the things on Earth, and we have the entire universe governed by the gravitational force. What else is there? Why is there two more spots? Well, remember we say physics take care of everything. So the bigger scale is astronomy, and physics has a force taking care of that, gravity. And the slightly small scale is electromagnetic force, which is chemistry. So that's about the material that we can see and touch, right? But what makes up those things? Proton, electrons, and neutrons, right? But what is inside the protons? Do you know that? Do you know the answer to that question? What is inside a proton? What is holding a proton together? Now that, and also, what happens when we break an element or break an atom, for example? Now, those give you something called nuclear force. If you want to understand that, you have to study something called nuclear force. And there are two types of nuclear force. There's a strong nuclear force and a weak nuclear force. Now, these are the forces inside the atoms. Okay, inside the atoms. So even chemistry will not study this, but physics, of course, study everything. So we will. But these are university level topics. Okay, so you will only look at this if you go to university and you study something similar. For example, if you study something like astronomy, physics, or engineering, then you might look at this again. Okay, so strong nuclear force and weak nuclear force is the forces that are holding the atoms inside together, holding the protons together, holding the nucleus together, which in chemistry usually you don't look at because it's too detailed. Okay, so that means in Physics 11, for us, the most important force this year is gravitational force. Now, let's move on. So, force of gravity is our main focus. So, let's talk about force of gravity. So, at this point, you might have an idea that, hey, gravity is the force that Earth extracted onto everything else, including us. But that's only half of the definition. The actual the official definition of gravity is actually this. Gravitational force is a force that attracts. Okay, now gravitational force can only attract things. It cannot repel things. Like, for example, two electrons electrically can repel. Electric force can repel. Gravity can only attract. It attracts all matter to other matter. All matter to other matter. Now, what does that mean? What it means is that gravity attracts anything to anything else, as long as you are massive, or not massive, as long as you have mass. So, for example, you can have like a big, giant watermelon on one side and a small kiwi on the other side. The watermelon and the kiwi are actually attracted to each other. Or alternatively, you can have like a person on one side and you can have like a pencil on the other side. And yes, they are attracted to each other too. Now, you might say at this point, Mr. Chang, that's not true. I've never felt myself attached to a pencil. Okay? Like the pencil is on the table, it's not jumping to me. How can you say that I'm attracted to the pencil? Yes, you are. Okay? The force is so small for objects that are little, like a pencil and you. The gravitational attraction between the two of you is so small that you cannot feel it. But when you have a gigantic amount of mass, for example, like the Earth, then its attraction to you is noticeable. That's why you cannot escape the Earth by jumping, right? No matter how hard you jump, unless you have like a rocket propulsion engine. So gravity depends on mass. The more massive you are, the more gravitational force you can extract on other things. But gravity is also a mutual force. That means is you attract someone, someone also attracts you. For example, the force that Earth is attracting onto you is also the force that you are attracting the Earth by. It's the same amount, but just through different objects' point of view. So what is mass and what is weight? Now, these are definitely going to come up in the multiple choice question as a very major concept about physics. Mass and weight are used very interchangeably in our everyday life. Someone asks you, what's your weight? And your answer would be 50 kilogram. But you have been answering this question completely wrong. Okay? You have been answering this question completely wrong. They ask you what is your weight, and 50 kilogram is not a weight. In physics, weight and mass are completely different concepts. So let's start with mass. Mass is the amount. Now, this is my definition, so it's, it's not like official word, right? But I think it's easier to understand. Mass is the amount of matter. Okay. Now, what is the matter? What is the matter in you? What makes up you? Well, elements, right? Everything you can see are made up of the elements. I mean, human being, for example, is made up of mostly carbon, some water, so H2O, hydrogen, oxygen, nitrogen, but it's mostly carbon. We're just like carbon for most, right? So that means, what are we really? What is inside carbon and water and anything? Well, proton, positively charged, neutron, zero charge, electron, negatively charged. That's what we are. That is what anything is. A whole bunch of proton, neutron, electron organized in a way that makes us us. You, if I break down every single element in you, I will get a soup of proton, neutron, electron. If I break down every single element in a pizza, I'll get exactly the same thing. You are made of the same thing that makes up pizza or anything else. There is nothing that's in you that's not in a pizza. I'm not kidding. You're all proton. We are all protons, neutrons, electrons. Anything is proton, neutron. The door in your room right now that you're looking at, right? Look at that door. That door is made of wood. Wood is organic. It's made up of like 80% of the same thing that you do, exactly. But if you break down into it, I mean, it has a lot of carbon too. But if you break down everything into its finest component, you will find, shockingly, proton, neutrons, electrons is exactly the same thing that makes up you. They are orientated a little bit differently, so that makes wood. Another orientation makes you. But they are the same thing. Okay? Now, so how much proton, neutron, electron that an object is made of is the mass. Okay? The amount of proton, neutron, electron that an object is made of is mass. Okay? So every proton has a little bit of mass. Every neutron has a little bit of mass. Every electron, too, has a tiny bit of mass. When you add them all together and multiply by how many proton, neutron, electrons you have in your body, that makes up all the elements that makes up you, is your mass. So, now, answer this question. What is your mass on Earth? Now, the answer would be 50 kilogram, 60 kilogram, 70 kilogram. Mass is measured in kilogram. Okay? Mass is measured in kilogram. So, every proton, neutron, electron in you is a small amount of that kilogram, and then you multiply. So, if they say your mass is 50 kilogram, that's how many proton, neutrons, electrons you have. So, what is your mass in space? Now, some people are thinking, 0, Mr. Chang, 0. You are massless in space, right? No. If you heard something like that, think about what was the term that was used exactly. Not massless. You are weightless in space. You're never massless. Massless means you does not exist. As long as you exist, there is mass. Actually, if your mass is 50 kilogram on Earth, your mass will be 50 kilogram across the universe, no matter where you are. Because mass is what makes up you. what is the only way to actually lose mass very quickly? Cut off an arm. Then you will have less mass. What is the quickest way to gain mass? Eat a turkey. You will gain the mass of the turkey in yourself. Okay? Mass cannot be changed just by moving your location. Mass has to be constant because mass is how much stuff you have in you. And that is not a number that changes unless you eat, right? So when someone asks you, hey, what is your mass on the moon? Exactly the same mass that I have on Earth. Why? I didn't lose an arm on the moon. Okay, maybe if you did, then you can say your mass is less on the moon, right? Or if you're wearing a giant backpack, then you add that to it. So that is your mass. It's the same no matter where you are. Your weight, on the other hand, now weight, which is the question that people ask, and then sometimes you'll answer with 50 kilogram. No, you shouldn't be. Because what is weight? Weight has to do with gravity. So let's say you have the Earth in here, right? So that's Earth. Okay, and then you're standing on here. Now, so what we said before earlier was that, there is something called force of gravity, and it's pulling you down to the middle of the Earth, right? So that force pulling you down to the middle of the Earth, that force right there, this is your weight. It's the amount that Earth is pulling you down by. It's the amount of force of gravity that the Earth is pulling you down with. That is your weight. Okay, so let me write that in here. Weight, okay, so weight is the force of gravity. So the force of gravity, the gravitational force, which is, we have a shortcut for it. It's called FG, F subscript G, right? Force of gravity. So we just have other forces going on. So, using subscript is a good thing. The force of gravity, okay, on an object. Okay, and that is your weight. So your weight, now, and that is measured in Newton. Okay, it should be measured in Newton. It's a force. So your force of gravity will change depending on where you are. Now, generally speaking, the more massive you are, the more massive the object that's attracting you are. For example, the Earth, the more your weight. So for example, on Earth, if you weigh 10 kilogram, right, on Earth, if your mass is 10 kilogram, then the Earth will pull you down with approximately 100 Newton of force. Okay, so the number on the left is your mass. The number on the right is your weight. Now, and this is only true on Earth because force of gravity is different on different planets. I mean, that is logical, isn't it? The bigger the planets are, the more they will suck you down with the powerful force of gravity, and the more you weight. So for example, you actually weight only like 20% or like 18% of what you weight on Earth if you go to the moon. That means when you go to the moon, you suddenly become very light. You can jump 6 times higher, for example, right? Everyone can dunk on the moon. Like if you have a basketball game on the moon, everyone can dunk. No one will shoot 3-pointer because everyone just dunk, right? So your weight changes depending on where you are, because your weight is the amount of force of gravity pulling you down, and it depends on where you are. So for example, on Earth, your weight, if you're 50 kilogram, right, your weight is about 10 times more, which is 500 Newton approximately. So that means when you land on someone, it's like 500 apple land on the other person. Okay, you weight approximately 500 apple. That's what I'm trying to say. Okay, so now that's average. I mean, for example, for me, I weigh a lot more than you do. So maybe for me, I weigh 80 apples, 800 apples. So let's say my mass is 80 kilogram, right? Then my force of gravity is going to be, the force of gravity on me from the Earth is going to be 800, 900 Newton. So I'll weigh as much as, 900 apples. So when I sit on someone by accident or fall onto someone, it's like 800 apple hit their face. Okay, instead of 400 apple hits their face. So weight changes. Weight is the amount of force of gravity pulling you down. More massive, more weight. Usually that's true, but mass cannot change. So when you're in space, very far away from the Earth, you feel weightless because you don't feel the force of gravity pulling you down anymore. You're far away enough, right? So you feel weightless. You will never feel massless. Massless means you die. Well, not die. You disappear from the existence of the universe. You disappeared. Okay, so how do we get that 50 kilogram is approximately 500 Newton force of gravity? Now, this is going to be from an equation that's on your formula sheet. Force of gravity is equal to mass multiplied by, so force of gravity is denoted Fg right here. Okay, so the equation is pretty simple. Mass times little g. Wait a second. Is that the same little g that we used in chapter 1? Yep, it is. That's the acceleration due to gravity. So that's the 9.8. Okay, so it's in meter now. So usually, of course, you can measure in meter per second. That's one of the acceptable units. But sometimes this is also called gravitational field strength. So gravitational field, so gravity field. So it's like a force field of gravity, the strength of that. Okay, so gravitational field strength. It's the same idea. Okay, so there are two units for this little g. Now, of course, we know that on Earth, that number is approximately 9.8. But, if you look at the equation, right, so that means g is equal to force over mass, right, if you solve for it. Now, force is measured in Newton. Mass is measured in kilogram. So you sometimes see people using Newton per kilogram as the unit, but they're the same. Newton per kilogram, meter per second square is the same thing. Now, of course, m is for mass. And I don't think I need to remind you, mass is measured in kilogram. Okay. Now, so about little g. So how come I'm not writing down 9.8 in here? Oh, because we will have a section in here to talk about it in more detail. Now, little g changes depending on two things. Little g is the strength of the force of gravity, right? So it depends on. Now, for example, I'm assuming that you are standing on a planet. If you are trying to measure little g. So it depends on the mass of the planet that you're actually standing on. So for example, it will be Earth force. Okay. Now second, it also depends on how far away you are from the planet. Remember, if you get really, really far, you can't really feel the force of gravity, and then your acceleration will be zero, right? You're not even attracted to the planet. So it also depends on the distance to the planet's center. In physics, we always count center, like the center of the planet, not the surface of the planet. Okay, so the distance to the planet. So it's very easy. The more massive the planets are, the higher the acceleration value. Okay, which makes sense. The more force you have on you, right? Second, is the further away you are from something, the weaker the force of gravity will be. That also makes sense. It's like a fire, right? Think about a fire. So a fire, when you walk close to a fire, you feel the heat. Now, but you walk far away from it, the heat is less, right? So gravity, same thing. If you're far away from the object that's generating that heat gravity, then, you feel less of an effect on it. So, for example, little g is equal to 9.8 meter per second square on Earth, near the surface at sea level. If you have to go really, really far away, that 9.8 number doesn't really work either. For example, if you live on like the Himalayas, the mountain, right, very high up in the sky, if you're trying to measure force of gravity at that point, right, it will only be 9.76 or something. I believe that. Like I remember reading it somewhere. So it's actually like a few decimal point less. If you go high enough, okay, on Earth. Now, but of course, the moon, okay. Oh, one thing in here, you realize we don't have a negative in here? Yeah. So when we calculate a force, we can use a diagram to represent their direction. So remember, if you're using diagram, usually you don't put the negative because it will be confusing sometimes. Yeah. So for gravity, when someone say, "Oh, what's your weight?" you don't say negative 40 like negative 500 Newton, right? You say 500 Newton. So, yeah. So you don't have to add negative to this one. Now, on the moon is about 6 times weaker than us in terms of gravity. So on the moon, the force of gravity is approximately 1.6 meter per second square, which means you can jump 6 times higher. You can lift an object that's 6 times heavier than what you could on the moon. So for example, if on Earth, you can lift 1 bicycle at most, then on the moon, you can do 6 bicycles at one time. Okay? Because that means something, that an object is 6 times lighter on the moon. The weight of an object is 6 times lighter on the moon, but your muscle is still the same, right? So if your muscle can handle 1,000 Newton, it can still handle 1,000 Newtons on the moon because that's your muscle. That's not going to change, right? But if the object that you're trying to move is lighter on the moon, so you end up being able to lift more. Now, Jupiter, on the other hand, is a much bigger planet than we are. So its force of gravity is also pretty big. So these are just some examples. You do not have to memorize the force of gravity for different planets, right? Except for Earth. Like Earth, yes, you have to memorize it. So on the sun is the most massive celestial bodies around us, and its force of gravity on the surface is actually 28 times bigger than that on the Earth. Okay, so for example, on Earth, you can easily pick up a basketball. But if I put that basketball on the surface of the sun, let's assume that the sun is cold enough for you to actually do that and have a surface, which it doesn't, and it's not cold enough. But let's assume that the sun is like a solid sphere with the same mass, and I invite you to have a basketball game on the sun. You wouldn't even be able to pick up that basketball because it's going to be 28 times heavier. Okay, so that basketball suddenly feel like a car, or at least like a bicycle. Okay, so now, so this is going to be something that you can change a number. So for example, so what is your mass in when your mass is? So let's say your mass is 54.5 kilogram, right? I'm making up that number. You can change it to your own value. If you only know your mass in pound, then you can do a conversion. 1 kilogram is 2.2 pounds, if you want. So what is your weight on Earth? Now on Earth, we should use mg, but with the little g replaced by the Earth gravity number, which is 9.8, right? So we do like 9.8 like this, which is approximately 10 times. That's why we say like it's approximately 10. So 534.5 Newton. So that's how much you weigh on Earth near the surface. So this is your weight. Okay, so now moving on, what is your weight on the moon? Now remember, your mass doesn't change. So your mass is still 54.5 kilogram. But what does change is, well, your weight on the moon. So the gravitational accelerations on the moon, which is 1.6, about 6 times weaker than that on the Earth, right? So remember, we make that remark earlier. So on the moon, you will only weigh 87.2 Newton. So you're going to weigh 6 times less. But your leg muscles are as strong as it is on the Earth. So therefore, you can jump 6 times higher. Nice, right? How about on Jupiter? What can you do on Jupiter? So on Jupiter, your mass is exactly the same as anywhere else in the universe, but Jupiter's gravity is really, really strong. 24.5 meter per second square is more than double of that on the Earth. So on Jupiter, you weigh 1,335 Newton. Now that means on Jupiter, you will find it extremely, extremely difficult to even walk, right? It's like you're wearing a jacket that is filled with sand on you, and then you try to walk with that. It's super, super heavy. So this is a little activity that we'll usually do in class, but it is now not possible to do because you don't have the kind of equipment. Basically, this exercise is about measuring how far you can jump, like how high can you jump on Earth, and then try to change that number to the same situations. Okay, so if you can jump that fast, that high on Earth, then how high can you jump on the moon, and how high can you jump on the sun? So we're going to use some make-up numbers, I guess, for this to work. Okay, so first, usually when we do this lab in class is I will have someone take a video of another person, your partner, jumping and try to measure from the video how high is the jump. So how high can that person jump over? So for example, right now, we're making these numbers just as an example. So let's say on Earth, you can jump over, so let's say, straight leg, you can jump over 30 centimeters, right? Okay, which is like the size of the ruler that I was using during the mini reaction time job lab. That's about 30 centimeters. So let's say you can jump 30 centimeters, which in standard units is going to be 0.3 of a meters, right? On Earth, okay? Now, so from that, I can figure out what is your re-initial, which is how fast were you jumping. So like when your leg was like this, right? At the beginning, you jump up. So there must be a re-initial. Now, and then at the end, you arrive at like the highest point. And then you come back down, right? So at the end, you arrive at the highest point. So let's say this highest point right here for you is, 30 centimeters. Okay, so that's your highest point. Now, I know you can use any number that you see fit is if you know your vertical. Let's say you're in the basketball team and you actually know your vertical, which is how high can you jump extra, then you can use that number instead of 30. I'm just making that number up, okay? I know 30 is a little low, but I'm making it up. So re-initial. Oh, I put 0. That's scary. Is unknown. I don't actually know, right? No way to measure that. Displacement, okay? Now, so I can jump 0.3 meters. So let's put 0.3. I'm jumping up, so it's positive 0.3. V final. Hey, what is the V final when you're at the top? Haha, that's like the one time that you can actually say 0, right? And acceleration. Okay, negative 9.8. Oh, Mr. Chang, why are you using negative again? Because we're doing kinematics again, that's why. So, yeah, you still need to do kinematics sometimes in this chapter. You think you can just forget everything you learned in the first chapter? No, you cannot. The laws of nature doesn't work independently. They work together. Okay, so to figure out your re-initial. Now, the reason why we want your re-initial is because, remember I said that your muscle doesn't change its strength because you move to another planet, right? Your muscle get its strength from you exercising, from you like doing all these stuff that, from growing up. So your muscle, unless you spend a very long time in a planet with very weak gravity, then your muscle will degrade. Your bones will degrade. Yes, that's true. But for example, so right now, if I just teleport you to the moon, you are as strong as you were just a moment ago when you're on Earth. But the gravity is weaker, so you can jump higher. So I'm going to assume that your muscle is exactly as strong when you move to the moon and when we go to the sun, right? So I need to find out how fast you can jump on Earth. That means, what is your initial speed? And we will keep that initial speed for the next two part when you're on the moon. We're just assuming that you're as strong as on the moon than you're on Earth, which is a good assumption, I think, fair assumption to make. Okay, so I want re-initial. Now v final is 0, so that takes care of this. Re-initial square and 2 acceleration negative 9.8 and displacement 0.3. Okay, now if I put that in the calculator, do a square root, do all this like crazy stuff, I'm going to get a re-initial of approximately 2.42 meter per second. Okay, 2.42 meter per second. So that's how fast my initial takeoff speed is when I'm on Earth. Okay, so that's re-initial. Now re-naught is the same thing as re-initial, just a different like initial, right? 0, the first thing. So 2.42 meter per second. That's my re-initial. Okay, so we're gonna have that number. Okay, we're gonna have that number borrowed to the second and the third question. So let's assume that our muscle is still as strong as it was on Earth. So our initial jumping speed is exactly the same. But what is different in here is the acceleration. On the moon, the gravity acceleration is negative 1.6 meter per second squared instead of 9.8, right? Now on the sun, that is very big though, right? It's like 274 meter per second square. Now, so how far can you jump? So what is your maximum jumping this height? If your V final is 0, of course, right? You're jumping to your highest point, so your V final is always 0. So then, okay, so you're just solving this equation for your V final. Now, we don't need to get time. I mean, obviously the time, we could get time, but let me do it for one. I mean, it's just a practice question, right? So how do we get to the, so for example, how do we get to the displacement? So we can use exactly the same equation, except we're solving for displacement, not solving for like V initial in this case, right? So V final square, V initial square plus 2AD when we are solving for D, okay? And that's it. So V final is 0, V initial is 2.42. Oh, I forgot the 2. 2.42, isn't it? Yeah, 2.42. 2.42. Okay, and square that. 2A, so 1.6, and D. So we're looking for D. Okay, some algebra later. D would be 1.83 meter. So your maximum displacement, that means the maximum heights that you can jump over, is taller than a regular high school student. So you can easily jump over someone. Not even splitting up your leg. You can jump over them with your leg like completely close to each other and just jump over a person. Like, because 1.83 I think is taller than the average height of a high school student, right? So yeah, that's pretty amazing, right? You can jump over someone on the moon just by jumping regularly. Now, and plus, remember I said that 30 centimeters for vertical is like a small, it's like a lower estimation for people who are not an athlete, right? If you're a basketball player, if you're a badminton player, if you are like a goalie, right? If you're for like a soccer goalie, if you're anyone who actually do practice jumping a lot, your number is probably a lot better than this one. Like it might be 60, it might be doubling that. That means you can jump over like 2 people. If you're jumping on the moon instead, right? Now, so the same calculation, I'm not going to bore you with the calculation because it's exactly the same. I just want to show you the number. The same calculation done on the sun is going to let you this value. You can jump this height, 0.0106 meter. Well, you might be saying, okay, what is that? Now let's try to multiply by 100 because, you know, if you multiply meter by 100, it gets you cm. And maybe cm is easier to understand, right? So cm, 1.06. Oh, 1 cm. You can jump 1 cm. Take our ruler and look at 1 cm. You can jump 1 cm on the sun. Now, if you can go to the sun and not die from the heat and find a place to land, none of those things are possible, by the way. But imagine that it is, right? Then you jump on the sun and you jump 1 centimeter off the ground and then you land. Okay? That's how sad it is. That's how sad it is. Okay? All right. Now, moving on. Almost done. Okay. So we do use the word G forces, like how many G, to measure accelerations experienced by an object on Earth. Now, so for example, right now you're sitting down and you're experiencing exactly 1 G. That means 1 times the force of gravity. Okay? 1 G is 1 times the force of gravity as an acceleration on you. So for example, when you are in a car and you're speeding up, you actually experience more than 1 G sometimes, right? Because your car could be moving forward. So for example, so that's just like a measurement system. I want you to think about it this way. So for example, if there's a car and the car is accelerating, right? Not the speed of the car, but it's speeding up. So if the acceleration is 4.9 meter per second square, then how many G are you experiencing? That means how many times of force of gravity are you experiencing sideways? Now remember, we usually experience gravity from the top down, right? So our bodies are used to it. But gravity sideways is like you lying down so that the gravity is pushing you down. Okay? So when you're in a car, it could feel like that, right? Your car is moving forward. You feel like there's a force pushing you backward. So how many times is that force pushing you backward compared to force of gravity. That's what the term how many g is the force or is the acceleration. So for example, a force that is 4.9, acceleration that's 4.9 meters per second square is half a g. So 4.9 divided by 9.8, so that's 0.5. So we call that 0.5 g. That means, hey, the acceleration of the car will feel like about half of the force of gravity, but it's going sideways. Okay? Because regular force of gravity is going, if you're standing, right, it's going from the top to the bottom. But this one's going sideways. Now, during liftoff, so let's say you become an astronaut in the future, and then the space shuttle lifting off, right? During that liftoff, there's a moment in time where the acceleration of the rocket and everyone inside in it, the astronaut, is actually 28 meter per second square. Now, 28 meter per second square divided by, on average, 9.8 meter per second for 1 times force of gravity is actually 2.9 g. 2.9 g. So that means during the liftoff of a space shuttle, the amount of force of gravity your body experiences is actually almost 3 times what it would experience normally. Now, what does that do to your body, though? What does that do to your body? It depends. It depends on how physically fit you are. On average, a normal human being, now that's what the next question is talking about. On average, a normal human being can actually withstand approximately 4 times the force of gravity. Now, what happens when it goes over 4 times the force of gravity on you? That means, let's say you go into a rocket or a car or an airplane and it's accelerating. If the acceleration is 4 times bigger than 9.8, which is the force of gravity acceleration value, then your body starts to malfunction. I should say it this way. So for example, some people will feel nauseous and they want to throw up. A lot of people will feel that actually. Some people will feel lightheaded, right? Because the blood is trying to go up, but then your body is moving too fast, so your heart is having trouble pumping blood to your head, so you feel lightheaded. And some people will just plainly pass out. That's actually a very common thing. When your body withstands an acceleration that's 4 times more than the force of gravity, normal people usually pass out and feel very bad about it if they don't pass out, right? Even if they don't pass out, feel very, very bad about it. Remember, look at your body, in this sense, right? Your heart is in the middle, your head is at the top. So that means your heart is pumping blood against force of gravity to your head. So if your whole body is accelerating upward, that means your heart is now fighting not just 1 times the force of gravity, but whatever acceleration you put yourself through in addition to that, right? Your heart is only as strong. It's a pump. It's a pump, right? Your heart is basically a pump. It can only pump so strongly. It only has a certain amount of force. So when your body is moving upward too fast or sideways too fast, too much blood will go to one side of your body and not enough blood will go to the other side of your body. Okay? That's what happened. So for example, if you're driving in a car and then you're turning right really fast, right? So the amount of acceleration for you to experience at that point is that a lot of the blood that is in your body will actually get pushed to the left-hand side of your body. Well, then your right-hand side of the body is missing important nutrients, right? Remember, the blood go through your body is actually doing delivering nutrients and delivering oxygen, most importantly. So why does people pass out when the car is too fast? Or when they experience too many G's, in this case, it's because their brains are not getting enough oxygen. And what happens when your brain is not getting enough oxygen? Do you know why people pass out? Like in general. People pass out because your body thinks you're doing something stupid and it wants to shut you down so that it can regulate, the brain can regulate your body instead of you regulating your body. You know that's actually why people pass out. For example, people who for example, cover their faces when they breathe, they pass out because they have a shorter breath at the end, right? They lack of oxygen. So your brain is thinking like, why are we lacking oxygen? You must be doing something stupid. Let me shut you off. So you pass out, right? So same thing in here. When you're experiencing very fast acceleration, your body, your brain is telling the rest of the system that, hey, I'm not getting enough blood. Something is wrong. So my owner, which is you, is probably doing something stupid. You know what's the one thing I can do? I can shut off my owner. So shut you off. You pass out. Because once you pass out, you can no longer do stupid thing, and the brain can take control and your breathing return to normal. Now, of course, your brain doesn't understand that you're in a very fast-moving vehicle and passing out would be very dangerous for you. But that's what your brain do. It's a self-defense mechanism. If something's wrong with your body, you pass out. The brain takes over, right? So, with training though, now, so regular normal human being, 4 times force of gravity will be kind of like the maximum. But of course, people are different, right? Some people will pass out at 3 times force of gravity. Some people will not pass out at 4 times force of gravity, maybe 5 times, 6 times. It depends. With proper training though, you can go up to like 9G, 10G. But that's like military, astronaut level of training. And they do start by passing out. Like at the beginning of the training, they just pass out and then they get used to it, right? So, for example, for normal human, right? So the 4 times of force of gravity just means an acceleration that is approximately 39 meter per second square. So now these are not like set in stone number. I mean, obviously, right? Human body reacts very differently to different stimulus, and different people with different build, with different like health, reacts very, very differently. But this is like a general guy, right? This is a general guy. So like too much force of gravity, too fast of an acceleration on you. That means you're changing your speed too rapidly. Your body cannot actually stand that. Okay. So that's why, in a roller coaster, so when a theme park design roller coasters and other games, they actually do put dummies, right? Before the park is open, they put dummies on the ride and they measure the acceleration of the entire ride. And what happened is afterward, they will look at the data from the dummy with the accelerometer, like the thing that measures acceleration is called accelerometer, and they will see if there's any part in the ride where a person as passenger on the ride will experience more than like 3 times of force of gravity, just to be safe. If it goes over 3 times, some people pass out, right? And you don't want that, right? You go to Disneyland, you get on the ride, and then you pass out. That's not fun, right? That's not the happiest place on earth, right? That's the scariest place on earth, right? You go up, you don't know if you come down alive or not. That's scary. So theme park will avoid that at all costs. They will have, dummy. They will have they will install some kind of accelerometer everywhere to monitor the speed of the ride, so that you don't change speed too suddenly. But I mean, it's a very hard to balance stance when you think about it, because that acceleration is what makes the ride fun. Like if there's a ride that has like no acceleration, you move at constant speed at all time, would you actually pay for it? Okay, maybe you will, because that ride is actually called the Ferris wheel. Okay, the Ferris wheel is a constant speed moving ride, right? I mean, yes, but you won't pay a lot of money for it, right? Roller coaster is exciting, is thrilling, is different, and that acceleration is why it's exciting and thrilling and different. But too much of it, you pass out. Okay, too many G's, you pass out. Like 2.5G, good. 4G, not so good, right? Usually for a lot of people. Okay, so that's it. And I'll pause the video right here. And descriptions or everything else will be provided on the blog post. Okay, goodbye.